Hello, everybody. So this is Fang Li from Oklahoma Christian University, and also in this work I co-authored with Dr. Gupta from University of Texas at Dallas. So our title of this work is called "Computing Supported Models via Transformation to Stable Models," which is a system description. So first, let me introduce the introduction and motivation. So the first terminology is answer set programming. It's ASP, which is a declarative paradigm for complex combinatorial search. And basically, it is a non-monotonic version of logic programming. So it's founded on the stable model semantics, and which identifies solutions as minimal models satisfying rules. Okay, so in the answer set programming, atoms are false unless strictly proven true, right? So if you don't have the proof that it's true, then we consider it as false. It's called the negation as failure. So it's excellent for the optimal in solutions, but the problem is it limits discovery of non-minimal but logically consistent solutions necessary for exploratory reasoning. So here I always use an example for this is suppose you have the rule says there's a cookie, right? So if dog eats the cookie, then cat will eat, right? And also you have another rule says if cat eat the cookie and dog will eat it. So this forms a positive loop, right? So we can say as if dog then cat and if cat then dog is a positive loop. So in the positive loop, under the stable model semantics, we end up with getting a minimal empty model, right? So there's none of them will be able to eat, right? So and so this is a limitation, but because if we say both dog and cat eat, right? So it doesn't violate any rule, right? Say dog eat, cat eat. If you check the only two rules we have, right? If dog then cat, it's true, right? And another one, if cat then dog, it's also true. So this is the limitation of the minimality, because sometimes we might want to explore more logically consistent scenarios, right? Not other than the minimal model. So here is why supported models. So the modern applications often require exploring richer non-minimal solution spaces, right? So for example, software verification is testing the backup and the redundant states, not just the minimal scenarios, right? So another scenario is that the medical diagnosis, right? We want to capture something like the patients with multiple conditions, right? Not just the minimal explanation of symptoms. And also for the planning and allocation, so the designing robust plans with over provisioned resources to prevent single points of failure. So in this case, we need something more than the minimal model, right? So fortunately, it was already proposed back to the 1988, which is called the supported models, which relaxes minimality while ensuring every true atom is supported by a satisfied rule body, which is just like the example we used for the dog cat example, right? Now, since there's the supported models, right? So we must have the way to compute it, right? So the current way, the existing approach for computing that is using the Clark's completion, right? So it's supported models coincide exactly with the classical models of a program's completion, right? So we first get the Clark's completion and then apply the set solver on that to compute the supported model. So, but in this case, we need to do what? We need to first compute the Clark's completion, and then we need to use a set solver to solve it, right? So, and the limitation for the ASP practitioners is that we require their maintaining a separate set tool chain for that if you want to get the supported model, right? And it also requires the translation between logical rules and the propositional CNF, right? So this is the conjunctive normal form, right? So we need to do that, the translation, and also prevents the direct use of highly optimized ASP solvers such as the Klingo, right, or SCASP. Like, so they're for supporting the model generation. So those ASP solvers are highly optimized. It's pretty fast. It's high efficient. But if we want to get to compute the supported models using the classical way, right? So it's not so practical. Then here comes our solution, right? So our contribution is we proposed a transformation-based method enabling the computation of supported models entirely within the ASP paradigm. So, which means that we no longer need to compute a Clark's completion, and we just do something, do some trick on the original program, the ASP program, and we do some transformation, and we just apply the ASP solvers on this transformed program, ASP program. Then we're able to get the supported models. So it's a novel ASP to ASP transformation. It decouples conjunctive rule bodies using auxiliary atoms. And also it is polynomial time, it's efficient, linear scaling in the rule and atoms, and also it's a formal correctness. So in the paper we did proof of that, right? So it's a bijection between supported models of original program and stable models of a transformed program. So also it's we have a practical tool, which is we call it a Python preprocessor for Klingo. Basically it is a Python script to do the transformation. Okay? So here is the formal definition of our transformation logic. So the key insight is we decouple conjunctive bodies using an auxiliary atom. Here we use the DMR, representing the body of the rule R is disabled. Right. So here is a formal definition. The formal format is here is an ASP rule, the answer set programming rule. It looks like we got a head, we got the body, right? The body. The body, we got the positive literals, we got the negative literals, right? How we do the transformation? We first wrap the whole body with a negation, right? So we'll do this DMR for the whole thing. Then we add a not. We apply the negation, and within the DMR, we do the negation of every single literal. So this one means that for every positive literal, we negate it into a negative literal, right? For every single negative literal, we negate it into a positive literal. So note here, we use the for each, right? So this is every single one. For example, like this one, we will have a DMR if not L1. This is one rule. Then we have another rule as DMR if not L2. Another rule. Then DMR if not L3. Keep going on. So after our transformation, there will be no rules have multiple literals in its body. So every rule after the transformation will only have one literal. Right, only one literal. So this is, if you pay close attention, you might already found that we simply just like borrow the idea of De Morgan's law, right? So implements the De Morgan's law. The body fails if any positive literal is false or any negative literal is true. Right? This is the basic logic. So if you still feel confused, let's look at this transformation example, right? So this is the original ASP rule, which reads that P if Q, R, not S. So Q and R are the positive literals and the S is the negative literals, right? So this is the ASP rule. So after we apply our transformation, it will be like this. First, we wrap them with a DMR literal, which is artificial one. We created this one. You could name it whatever you want, right? So this is for, in our paper, I use this as our wrapper. So we say P if not DMR. For the DMR is, see, if for all the positive literals, we negated them into negative one. So DMR if not Q, and DMR if not R. So the S is a positive literal, so we negate it into it's a negative literal, we negate it into a positive. So DMR if S. So this is the new this is the new ASP program after our transformation. So if we, in this case, if we apply the ASP solver, for example, Klingo, on this transformed program, we will get the supported model, right? So if you apply the ASP solver like Klingo on the original ASP rule, you get the stable model. You get the ASP model, right? So this is one simple illustration of our transformation. Okay, so the how do we do that is actually we implement a Python preprocessor, right, which we integrate with Klingo, the Python library, right? So it's got a pipeline. So the first step is we have to ground the program, the original program. So this is also one of the limitations is our approach. We must ground the ASP program first. Okay, so we use the Gringo, which is as a part of the Klingo. So we use Gringo to do the grounding, and after that we do the transformation. Just apply the same the stuff like this, right? The Monken's law. We apply the transformation. We get our new transformed program. Then we compute the stable models using the Klingo. So on what? On the transformed program. So we get what? We get the supported models. Of course, because after the transformation, we have some artificial stuff, right? We added those artificial wrappers, right? So just like the parentheses in the Monken's law, right? We need to project out those auxiliary so that we only keep the original atoms. So this is the whole pipeline for our implementation. So the performance is minimal overhead, and the bottlenecks remain standard grounding and solving rather than the transformation step. Yes, grounding still is the bottleneck, right? But not our transformation. The availability, so we have made it public and open sourced on GitHub and the Nodo. So I think by the time of the proceeding of this conference, you should be able to see the link. Okay. So now by the end, I provide the application scenario, which is a simplified version from our paper. This is the medical diagnosis. So the physicians explore multiple co-occurring conditions. And so this one, for example, it defines like if it's infection, it's infection. If it's inflammation, it's inflammation. So these conditions can be hypothesized. So, and the symptom like this. So if the fever, right? If infection. So if you got infection, you will get a fever. If you got inflammation, you also get a fever. If you got an infection, you also get a fatigue like this. But if you use the ASP solver to solve it, you get a empty set. Why? Because here we got a positive loop, right? Those are got a positive loop. So positive loop in the ASP, the minimal model is just like the cat dog stuff, right? So in the stable model semantics, you cannot prove yourself. Right, by yourself. So those are called positive loops. In the positive loop, so you get empty model. It's not no model, it's empty model, right? So, but if we apply our transformation, right, we apply like those stuff, those like a DMR stuff, right, the wrapper. So then we apply the ASP solver on our transformed program. We get the supported model. So supported model have like this. You got an infection, fever, fatigue. You got an inflammation, fever. You got an infection, inflammation, fever, fatigue. Right? See, you got all of those. So if you check all of those, like this model plug in doesn't violate any rule, right? This one, if you plug in, doesn't violate any rule, and also does this one, right? So that means like we no longer need. So in this medical diagnosis, we are not satisfied with a empty model. We won't know that, hey, is there any possible scenarios, right? So those, for example, a patient might have this 3 or this 2 or this 4 at the same time. It's totally possible, right? Totally possible. So this is a application scenario. Now the conclusion of future work. So the summary is our approach bridged the gap between the 1988 theoretical semantics and the modern ASP solvers. We developed a formally verified the polynomial time ASP to ASP transformation, and also the enabled exploratory reasoning, redundant system modeling, and differential diagnosis natively within the Klingo. So the future direction, we want to integrate directly into the ASP grounder, right? So which handling the variables natively, and also extension to destructive logic programs, also incremental model computation and preference-based filtering. Okay, so that's pretty much what we want to present here. So if you got any questions, since this is a backup recording, so in case like the bad connection or the schedule confliction something, so the organizer requests us to pre-record a video on this. So if you got any question, and either you can email me or I believe Dr. Gupta might present at the time. So you're welcome to ask questions. So we'll try our best to answer your questions. Okay, thank you so much.